Hello Python programmers. In this video we build on our knowledge of NumPy to use a NumPy 3D array as an image and then manipulate the contents of that image. We're applying the concepts of how an image is represented to the structure of a NumPy array, and a 3D NumPy array maps very conveniently into an RGB image format. We can also store that 3D NumPy array as a graphics file very conveniently with one function call, and we can display that file in line with our notebook with another function call. So we're going to take what NumPy considers just to be a plain vanilla 3D array, and we're going to map conceptually the format of an image into that 3D array. And the third dimension will be red, green, and blue, the components of a pixel. So the third dimension will always be 3. And the way this works, I think, is convenient. If you think about our data structure, our NumPy array, think about it as a 2D array, and then each of those elements in the 2D array have 3 values. Instead of just a single integer at that location in the array, there's actually 3 red, green, and blue components at that location. And we'll use slicing to set values instead of having to step through the entire array 1 pixel at a time. But just to complete the thought, we will do a quick demonstration of stepping through the array 1 element at a time. We're going to use 2 different libraries to accomplish this. This is a brief introduction to the PIL library, Python image library, and matplotlib. I don't know how to pronounce it. I just call it matplotlib. But we're not bringing in the entire matplotlib. We're just bringing in the pyplot component. The aliases here are industry standard, so to speak. They're commonly used by developers. We alias the PIL library as image with the capital I. We alias matplot.pyplot as PLT. I have provided for you the Jupyter Lab notebook that we'll be talking about in this presentation. The first cell simply imports the 3 libraries that we need: PIL, matplotlib.pyplot, and NumPy. We can run that cell once, and then we know that those 3 libraries are now available to us throughout this cell. In slide 3, some background, what we plan to do. If you think about a graphics file on your disk, it commonly is referred to as a JPEG if it ends in JPG or JPEG, or a PNG file, PNG, or a bitmap, BMP. Those are all formats that use individual pixels and store 3 color values for each pixel: a red, a green, and a blue. And there are other ways to store image files too. There's a vector format that we're not going to get into, but these bitwise image formats adapt very well into 3-dimensional NumPy arrays. So think about the 3 dimensions in the array as row, column, and color. I'm going to present this as a 2-dimensional array, row and column, with 3 values at each point, at each intersection of row and column. That's the way that makes sense to me. We can load from the disk an image file into a 3-dimensional NumPy array. We're not going to do that in here, but we can. What we're going to do, like crazy, is manipulate this 3D NumPy array, and then with one function call, store it to the disk as a PNG file that you can read with whatever image programs you have on your computer. As we go through this presentation, we are processing more data than we have in the past. It does take a little bit of time. And we're also going to reach a point where we get hung up because the computer is waiting for us to do something, and I'll show you what that something is. And you're going to be well served by keeping track of the busy idle indicator in the lower left-hand corner of that tab. If it's idle, you're good to go. You can continue editing. Your program has done what it needs to do. It's finished. If it says busy, then you either have to take some kind of action to get it to continue, or you have to wait for it to finish its computation. So just get into the habit of glancing at that busy idle indicator, and you'll feel good about what your computer is doing or not doing. We'll start with a simple motivating example. We've done this before. We can print this. We can conceptualize this pretty easily. It's a very small 2x3 NumPy array. We're initializing it with a list of lists. The first sub-element in that list of lists is 0, 1, 2. That's going to be the first row. The second element is 3, 4, 5. That's the second row. It becomes a 2x3 array. We could also do it by calling the arange function, which is called arrayRange, and that builds a one-dimensional array, in this case from 0 to 5, and then immediately reshapes it into a 2x3, two-dimensional. So we're going from 1D to 2D in that line of code. Then we can print it out. It prints out conveniently. It doesn't take up a lot of space on the screen. It's easy to study. But then we can slice it, and this is going to be the basis for image manipulation, is effective use of slicing syntax. In this case, we're saying I want 0, comma, colon, and that's something that we need to be able to understand and to compose on our own. Remember, you'll be composing slicing logic to complete the assignment. In this case, 0, comma, the first axis, the first dimension, is what we think of as the row dimension. I want row 0, and then comma, colon. This comma is a separator between the two dimensions, between row and column. And the colon means I want all the columns. I don't care how many there are. I don't have to stop and think, are there 5, are there 10? I just put a colon in there, and that gives me all the columns. And then I can do an assignment statement. And this assignment statement simply stores the value 42 into row 0 and all columns in that row. And that's fairly straightforward to conceptualize, and it's easy to print. If I go back to Jupyter Lab in the notebook that I provided for you, there's that same code. I can run that code. The first thing it does is print out the original array that we created, and you can see it's got 2 rows and 3 columns. It prints out the shape, and we know it is 2, 3. We're just verifying that it's shape 2, 3. After we do the assignment statement, we can print it out again and see that the first row has been set to 42. If I want to set the first column to 42, I could edit this slicing syntax. I could say colon, comma, 0. And now I'm asking for all of the rows and the first column only, setting those values to 42. When I run that cell now, the first column has been set to all 42s. We're demonstrating then that in a small, very small, two-dimensional array, we can do slicing and then print, and we can see from the printout that we did what we thought we were going to do. Now this falls apart when you have arrays of any significant size and when you start adding dimensions. So it's important that you're able to visualize what's going on in this small scale test, because it gets harder in the bigger scale test. We're going to ramp it up to 3 dimensions. Here's where it starts to get interesting. On slide 6, here we're going to introduce our image, our concept of 3 dimensions inside the computer. Using a 3-dimensional NumPy array, And we're going to arbitrarily decide that the third dimension is the color of each pixel in that two-dimensional array. So a pixel, which stands for picture element, is a dot on the screen. You may know something about what we call the resolution of your screen. That's generally given by two numbers, rows and columns, like 1020 by 640 resolution. You may have seen that on a monitor, on the statistics for your monitor. Those are pixels, and they're usually given in two numbers, rows and columns. So that maps directly into the concepts we're discussing here. And that third number, what they don't give you when they talk about the monitor, they don't give it to you in this form anyway, is how many colors can be represented at that pixel. Now, in our world, we're going to represent a color with three components, red, green, and blue. That's why that number is 3. That third dimension is 3 for the amount of red, the amount of green, and the amount of blue that will live at each pixel. Those numbers can go from 0 to 255. So there are 256 different shades of red, 0 to 255, 256 different shades of green, and 256 different shades of blue. And if I get out my trusty Windows calculator, and I multiply 256 times 256 times 256, there are 16,777,216 different possible values that we can store in a pixel. A pixel can have 16,777,216 different colors on a screen, using 256 different values for each of red, green, and blue. Does that really matter to us here? No, it's just a little background information for you. Once I've created my three-dimensional array, and I'm starting out with the very simple one here on the slide. This is slide 6. I do a array range array, which creates a one-dimensional array, in this case from 0 to 17. So there's 18 elements in that one-dimensional array. It's linear, and they go from 0 to 17. Then I immediately reshape that into a two-dimensional array. And this works because 2 times 3 times 3 is 18. So I've got the same number of elements in my 3D array that I had in my 1D array, and that means I can reshape it. All right, what if I want to start dropping in some colors? Well, again, here I'm going to fall back on my slicing. Now this is a little bit subtle because even though this array has 3 dimensions, I'm only slicing 2 of them, and the third one is taken to be the entire third dimension, whatever it is. So look closely at this. I have 0, 2, 0, 3. That means I want rows 0 through 2, stopping before I get to 2, so that's row 0 and row 1. Columns 0 through 3, stopping before I get to 3, that's columns 0, 1, and 2. And at that location I want to store 3 things, and I can store 3 things at that location because it's a three-dimensional array. And here in this single line of code, we are demonstrating how we are conceptualizing a three-dimensional array into a two-dimensional array consisting of pixels that have 3 values. That's the bottom line right there, is what we're doing. So after we've done that slicing, this particular example is setting each pixel to red equals 0, green equals 0, and blue equals 255. We're saying no red, no green, and all possible blue. I want complete blue and nothing else but blue. Then I can print it out, and if you look at the printout on the slide, you can see that there are a lot of zeros and there are some 255s. It looks like we're on the right track. And the way this prints out is a little bit different because it's a three-dimensional array. It actually prints out the first row, and then it prints out the second row. So the first row consists of 3 values, but each of those 3 values has a red, green, and a blue component, and you end up with quite a bit of information printing out. There's 18 different numbers there. And I do encourage you to take some time and study that, because if you can grasp the concept at this small scale, then you'll have a much easier time writing your own slicing logic when you come to do the homework. If I go back to Note Jupyter Lab again, whoops, where am I? There I am. And I run the code from that cell we were just discussing on the slide. There's the output that we got. The shape is 233. Remember, the third dimension is always going to be 3. The first 2 dimensions are the size of the graphics canvas, I guess, that we're painting on. In this case, it's a very small canvas, 2 by 3, 2 rows by 3 columns. And the third dimension will always be 3 for red, green, and blue. The red, green, and blue components of each pixel in that 2 by 3 two-dimensional array. That's our trick. Third dimension is always 3, and then we slice the first 2 dimensions and store values into that third dimension. Let's scale it up. Back to the slide again. This is slide 7. Let's create something that we can actually work with. I'm going to make a 500 by 500 canvas. I'm going to create a linear 500 by 500 by 3. Remember that 3 is red, green, and blue. And then I'm going to reshape it into a 3-dimensional 500 by 500 by 3. I can print out the shape. I can print out the data type. I'm definitely not going to print out the array. That's 500 times 500 times 3. That's a big number, and that would do me no good at all to print that out. At this point, then, we have abandoned the capability of printing these things out and studying them. They are just too big. That's why those small scale examples were so important. Then, here's the part that I highlighted. I decided that the entire array, the entire canvas, should be red and blue combined with no green, and that's a pretty magenta color. If you have a T-Mobile phone, you've probably seen that color. My slicing strategy is colon, comma, colon, comma, colon. I want every row, every column, and every value in the color. Pretty neat, huh? Now that changes the NumPy array in memory, but that doesn't show me anything. In order to visualize what I just did, I'm going to say, take this 3D array that I've been conceptualizing as an image and display it as an image. So look, all the things that we've been studying in the last few minutes, the way we visualize manipulating this array, the library is also willing to visualize this 3D array the same way. It's willing to take that third dimension as red, green, and blue, and the first 2 dimensions as rows and columns. And we call a function called IMShow, passing it that 3D array, and it will create, in line with the Jupyter Notebook, a nice little plot of our 500 by 500 canvas. So go back to Jupyter Lab again. We've got all this wonderful code in here. And let's run it. And there we go. So relatively quickly, we get a pretty little plot of a bunch of magenta dots because of the willingness, the ability of the PLT library to conceptualize that 3D array as a graphic. And hopefully you're realizing then that all you're going to be doing in your homework is just slicing, 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 and storing, storing, storing strategic color values. All right, moving on to the next cell. I promised you we would do one brute force example. In this case, we're going to use random numbers. Therefore, I dragged in the random integer library. Actually, just one function from the library, randint. And then I create a 500 by 500 canvas, and making it 3 dimensions. Then my third dimension is red, green, and blue, so it's 500 by 500 by 3. And then I brute force it. And when I say brute force, I mean I go through and I touch every pixel individually. And I actually touch every pixel 3 times. I'm just showing you this because I'm contrasting it with the techniques that we've already seen, how easy it is to write one line of code to do slicing. And this is a little bit more complex because I have to build a nested loop inside of another loop and then explicitly touch each individual element in that 2D array. We're not going to do this together in the homework. I'm not going to require you to be able to write this kind of code. But let's run it just to see what we get. And there it is. We get noise, which we would expect. We ask for random values, and each of those random values became the red, green, and blue shades of a pixel. That's enough of that. Finally, I got a little bit creative, and this is the extent of my creativity. I'm not a graphics person, but I looked up something that was moderately colorful, and that is the Denver Broncos of the National Football League. They are orange and blue, so I thought, well, maybe I could reproduce the orange and the blue from the Denver Broncos uniforms. That sounds interesting. But before I run this code, let me take you back to the slide. And I skipped over the brute force thing in the slides, but we talked about that enough. So I skipped over slide 9. And there's my code to generate the Denver Broncos colors. It kind of looks like a flag, I guess. I realized that they are orange and blue. Okay, I've seen them play, so I know what their uniforms look like. And I just looked for a convenient way to create orange. And if you focus on the code on the slide, it's a little bit different from the Jupyter Lab, and I'll talk about that in a moment. But on the slide, I decided orange would be 255, 128, Okay. And I probably looked that up because I don't know enough about colors to have those things memorized. But if you take all of red and you put in half of green, you get orange. And then there's no blue at all. So 255 red, 128 green, 0 blue gives you orange. And that's the left-hand side of my flag, so to speak. On the right-hand side, I wanted blue, and blue's easy. Just turn off all the red, turn off all the green, and turn on all the blue. So 0, 0, 255 is all the blue and none of the red or green. My slicing strategy, and I'm going to flip back over to the Jupyter Lab and then talk about the slicing. Flipping back over to Jupyter Lab. Slicing is colon, comma, colon 300, and then I'm assigning that the value orange. So the row dimension is just a colon, which means all the rows. The column dimension is colon 300, meaning start at row 0 and go to column 299. I'm asking for essentially the left side of the graphic. And then to get the right side, colon, comma, 300, colon, again asking for all the rows and asking for columns starting at 300 through the end of the graphic. and I'm storing 0, 0, 255 in all of those values, which is blue. Okay, well that does the mathematical manipulation and creates our data set, our 3D array. Then in order to get that into a file on my disk, I simply call from array, and the from array interprets this data the same way we do. So it assumes that the first two values, the first two dimensions are row and column. The third dimension is the color of the pixel. So once I've got this thing in image format, I call img.save, I give it a file name, and that creates a file that I can load with MS Paint or whatever graphics program is convenient for me. And this is very cool because in about 5 lines of code, I am able to create an image, put some color in it, and then store it on the disk. When I run this cell, nothing happens. It goes idle very quickly. If you watch the lower left-hand corner of that tab, you might see busy flash up, but it does happen very quickly. It's a relatively small file, and I have a pretty fast computer. I have an SSD, so there's not a lot of processing that has to happen, but there is some. You can imagine if you were processing very, very large graphics files or doing a lot of mathematical manipulations, it would take some time to do that. And that's why I encourage you to keep an eye on that idle. If I look over in my File Explorer, there is the PNG file that I just created. I can double click on it. It loads into the Jupyter Lab notebook. Of course, I could go outside of my browser and I could open it using some other tool. It's just another disk file. It's very convenient, however, to be able to load into Jupyter Lab, and I can take a look at it and say, yeah, that looks like what I want. And close it again, go back to my development here and tweak the colors. And speaking of tweaking the colors, let's address why these are different than they are on the slide. On the slide, I used, as I mentioned, orange is 255, 128, and 0. Okay. But in the Jupyter Lab notebook, I used to get orange 251, 79, 20. And the reason for that is because there is a website called Team Color Codes, and someone has taken the time to define the RGB codes to get Denver Broncos orange. Somebody took the time to do that. You can buy paint. Oh, I didn't notice that. You can buy paint to match that color. If you're a serious fan of the Broncos, and let me say I'm not a fan of the Broncos. All I really care about is that the colors are kind of pretty. But maybe I should be using the Bengals today. But I can clone or copy these three values, 251, 79, and 20, into my notebook, as I did here to get the orange. And that gives me the exact hue, the exact shade of Denver Bronco orange. When you do your homework, you're going to be reproducing, and I have on the very last slide, or the second to last slide, a set of flags. You can pick any flag that you like. You don't have to pick from this list. All I want you to look for is a flag that has at least 3 colors to make you work a little bit. I would not recommend doing the Union Jack, the UK flag. That's a little bit complex. The United States flag, overwhelming. I mean, if you're ambitious and you're graphically oriented, sure, go for it. But their minimum requirement for the assignment is just 3 colors. But those 3 colors, do the best you can to get close. If it looks like red, just make it red. We're not grading you on whether you matched precisely the colors on that flag. I just want to see your ability to slice and your ability to create slices that approximate reasonably these flags. So don't spend 15 hours matching colors. You can see pretty easily that if it's a 3-color flag like Germany, then it's 3 evenly sized horizontal bars. Therefore, it's not a lot of work to create those 3 slices. And that's what you'll be doing in your homework. The homework is posted. So after you've watched this video and studied it, take a look at the homework and you'll be able to jump right in and get that done. Be sure that when you edit your code to create your flag, that you change the name of this file, because you won't be creating the Denver Broncos colors. You'll be creating some flag, and you might want to call it United States flag or some descriptive name like that. I'll leave that name up to you. But I hope this was useful and interesting. Good luck with your homework. If you have any questions, please post them in the FAQ. Thank you.